Okay, in this video, I'm going to be telling you about vector fields. So we've gone and we've started this class with a discussion of vector valued functions, and then we kind of switched gears and talked about functions that maybe took in a vector but gave you back a real number. We did our partial derivatives, we did our double, triple integrals, we did all that good stuff. And now we're going to be interested in functions that take in vectors and give you back vectors. That's a vector field. And what I'm proposing is, you've actually already seen this before a couple of times. We just haven't really done a deep dive on it. So a vector field is a function that's going to take in a vector and give you back a vector. So it's f, which maps Rm into Rn, at least for our purposes. Now, for the discussion in this video, m and n will both be 2, okay? And in this course, we're pretty much only going to be looking at vector fields where m is equal to n. But you can definitely have a situation where you would take, and we saw it in linear algebra, we can have functions that take R2 into R3, R3 into R1. We actually already did that. And I should mention that I'm interested in m and n both being bigger than 1, right? Because if they were 1, if m was 1, that's a vector valued function, right? If we're just taking the real line and mapping it out into some higher space, that's going to create a path. That was vector valued functions. Okay, if we go the other direction, if n is 1, that's a real valued function. That was what we just spent a whole lot of time doing, basically, most of this course. Okay, so I think what I need to do first is just write down a couple of examples and draw you a couple pictures of them so that I can convince you that you have maybe seen this before. Okay, so the first example I want is to just look at f of x and y is equal to 2 and 0. Okay, that means that, for any x and y, it's going to spit back this same vector that goes over 2 and up 0. So I can draw a picture of this pretty nicely. So at any point x and y, it just goes to the right by 2. Okay, so I'll just draw you a few of these. Whoops. It wasn't quite long enough. These should be all the same length. I realized those. Not really making them all 2, whatever that means. Okay, but I think this is a good image. Okay, I think maybe you've seen something like this before. I think a lot of times it's convenient to assume that certain fields in physics are constant. I think, but there are also going to be situations where you have inverse square fields. Coulomb's law definitely dictates some kind of vector field. Let me flip back in the textbook. So they had a long list of examples. Okay, we've got, gravitational fields, electric force fields. Both of those are inverse square fields for reasons that I will leave to scientists. Okay. I think, I've shown you a constant function. Now maybe I'll show you a slightly variable function that I found kind of interesting. Maybe I'll switch this to be f of x and y is negative x and negative y. And I kind of like this example because, hold on a second. It kind of necessitates us to start to think about different values of x and y. And so what I can do is I can make a little 3-column chart. So x, y, and f, which depends on x and y. But it's really not very complicated. You just take x and make it negative, and you take y and make it negative, and you turn it into a vector. So at the point 1, 1, the vector is negative 1, negative 1. Okay, so if I start at 1, 1, and I'm going to the left by 1 and down by 1, I'll go back to the origin. And actually, I'm going to use a different color for this because it's going to start to get a little loud. All right, so I'm over here, and I'm going back to the origin. And we'll look at, maybe 2, maybe, how about negative 2 and 3? So that would be over here, somewhere about right there. Maybe like that. Figured not going to be drawn to scale. Okay, so the vector that I get when I run this through f is going to make x negative, so that's positive 2. I'm going to make y negative, so that's negative 3. which means I'm going to go to the right by 2 and down by 3. And hopefully after these 2, you're seeing the pattern that it's just going to map a point back, you know, the vector we get is going to point right back to the origin. So I can go back and I can do that. Okay, see, this is getting a little noisy. Doesn't really look like I want it to. What I'll say while I'm drawing this is that 2D vector fields, they're okay to draw. I mean, provided that this is reasonably nice. 3-dimensional vector fields, not something I'm going to attempt to draw for you here. I could go in and I could draw you x, y, and z, and I could say, you know, I could do maybe a constant function where probably would be easiest for me to draw if it was just like 0, 0, 1 or something, and just be always sticking up by 1. But I don't think that would be very interesting, and I'm going to save the discussion of vector fields in space to the next video. Okay, so I think maybe, let's see. I'm going to do, oh no, I'm going to stop and I'm going to say, wait a second. We've seen this before. It sure seems like we have. We've seen a plane with what looks like kind of vectors on it in AP Calculus. And we said that we looked at slope fields. And then that's kind of what I want to call back to, is that an example is the slope field. So what I would say is that, you know, dy dx, it was a slope. And so the way we drew them was that we kind of always made the length equal to 1, just to, so it wasn't again too noisy. But that was in a sense a vector field. And then also the gradient, and that's what I really wanted to tell you, was that, you know, we've talked about the gradient of a function, you know, in this class. And I may have at the time mentioned that it was a vector field, but remember that, you know, for a function f of x and y, and maybe I'll say z equals f of x and y to just remind you that this lowercase f I'm talking about is a real valued function, right? It takes in these two, but it only gives you back one number. Okay? And we said that the gradient of z was equal to the partial of f with respect to x and the partial of f with respect to y. Okay, well, the partial of f with respect to x and the partial of f with respect to y can both be functions of x and y. Okay, so really it is a function that takes in x's and y's and gives you back a vector. Okay, that makes it a vector field. Okay, now I'm going to point you towards a different example that I'm going to probably like plot it or write it down, and then I might pause the recording so I can draw a pretty good picture of it, because I don't want to draw it the wrong way, because I want it to kind of drive the next discussion. So I'm talking about g of x and y is equal to y and negative x. Okay, so y and negative x. And, you know, usually we're going to say that g, just to remind ourselves that g is a function that's going to give us back a vector. I'm going to put a little, you know, vector thing over it. Okay, so I'm going to prepare to draw this. And I think rather than making a chart and actually trying to plot it accurately, I might try to convince you of what this looks like with some algebra. Let me think about this for a second. Yes. Okay. So, and this is actually what they did in the textbook, and I think that it'll be a much faster way to go. Let's think about, just like, where are these vectors the same length, right? This could help us sketch our field. So, where is the length of G a constant? Is the question. And we know how to find the length of a vector. We take its components, we square them, we add them, we take the square root. Okay, so this is y squared plus negative x squared is going to be x squared is equal to some constant. Well, this is a circle, right? Okay, so any place where we're sitting along some, circle, all of the vector field vectors are going to have the same length there. Okay, so I'm going to start with maybe just two kind of nice circles, maybe circle radius 1 and circle radius 2. Hopefully this would show you what I'm hoping. So I'm going to just real nicely draw a pretty faint circle there. It's supposed to be a good one, but it wasn't that great. Right, not the best I've ever done, but certainly not the worst either, and it'll be good enough for us. All right, so this is going to be, at 1, and that'll be at 2. Okay, so let's just think about a couple of vectors along the main unit circle, like probably 1, 0, 0, 1, negative 1, 0, 0, negative 1. All right, so at 1, 0, I'll have the vector 0, negative 1. Okay, well, I can do that. Okay, at 0, 1, I'll have the vector 1, 0. Okay, at 0, negative 1, I'm going to have 1, or 0, 1. And then down here, you can kind of see the pattern. Okay, it's going to go like this, but flat. Try to get that right. Okay, and then I think what you would see at 2 is that you would have twice as long of vectors. Okay, so it's just going to be kind of the same thing, but twice as long. Right, and you could maybe just mentally fill in the rest of the picture. Okay, but what I want to tell you is that I want to remind you of a fact that I actually proved for you, quite a few videos ago, is that the gradient of a function sits normal to its level curves. Okay, and this is a vector field, and it's looking, maybe not exactly normal to this circle, but if you think about, a circle, if it's tangent to the circle, then it's normal to the radius. Okay, and you can see, so really what's happening, and maybe I'll put in a couple of more of these. You can see it's kind of clearly indicating some sort of clockwise orientation here. So I'm just going to go and I'm just going to make sure it's, thinking width or length 1. Wasn't maybe the best I've ever drawn, but I can just go and I can draw a kind of a little radial line here, and we know that a radius is perpendicular to the tangent to a circle at the point of tangency. And so, if these were the level curves of some function, that were sticking out radially, well then, we could say that g was the gradient of that function. And that's kind of what we're getting at here in this discussion. And the reasons why we're interested in a vector field that is actually the gradient of something else, I think will become more evident as we move through the content. I don't think I'm going to try to stand here and convince you of the merit of conservative vector fields. I haven't defined that yet, but I'll just kind of show you the test for it here, work with it a little bit, and then we'll move on, and over time we will see its use. Okay. Okay, so the second thing I need to tell you is the definition of a conservative vector field. Vector field f is conservative if it can be expressed as the gradient of some other function, some other real valued function. Okay, so we say that f is conservative if f is equal to the gradient of some other function. Okay? Now, I will tell you that we will call this the potential function. Okay, this lowercase f that is a real valued function. Specifically, F is probably going to need to take Rm into R, to match up with that. But I'm just going to also mention that that is called the potential function. And I think physicists might be able to, find some meaning in that. So, what was I going to say? Okay, I think next, what I am going to tell you, just without kind of jumping in and talking about what is and isn't conservative, I'm going to relay to you a theorem that's going to be useful for us for vector fields in the plane. A vector field is conservative, and probably I need to be a little more specific about what does this look like, because I'm talking about a vector field in the plane. So F, which is equal, well, maybe I'll just be very explicit, F, which takes in x and y, is given by some function m of x and y, and some other function n of x and y. Okay, this thing is going to be conservative if and only if, and I'm only going to be able to prove one of these directions for you, the other direction. If I remember to, I would have to use Green's theorem. I looked it up in the textbook, and I think once you know that theorem, it's not that complicated. I just don't have the tools yet to prove the other direction. So conservative if and only if my is equal to nx. If the partial derivative of this thing with respect to y is equal to the partial derivative of this thing with respect to x. Okay, so if my equals nx, for all x and y in some sort of domain that I suspect needs to be connected, but that's beyond what we're doing here. Okay, so to prove this, I'm going to prove that if it's conservative, then this happens, which is actually the less useful of the two directions, but I think the other direction you're going to have to just take on faith for now. So I'll be showing that if f is conservative, then my equals nx, and this is very easy. So what I'm going to do is I'm going to just kind of remind you that I'm showing that direction, the forward direction of the implication. And I'm going to say, suppose that f is conservative, which is to say that f is the gradient of some other function, some potential function. So suppose that gradient field f is equal to the gradient of some other function. Vector field f is the gradient of some other function. Okay. That means that, and if we're saying f is still this m and n, well, the gradient of f is equal to the partial of f with respect to x and the partial of f with respect to y, right? So I've got fx and fy. But I also have already defined large F to be m and n, which is to say that m equals fx and n equals fy. Okay, so fx and n equals fy. Okay. I'm going to take the partial of m with respect to y, because that's what I'm interested in showing, the two things are equal. And that's going to be fxy. And then I'll take the partial of n with respect to x, and that's fyx. And the Claro theorem tells us that those mixed partials are equal, provided that these functions are any sort of reasonably well behaved. And so I'll write that. So my equals fxy, and nx is equal to fyx. Therefore, my is equal to nx by the equality of mixed partials. Okay. So that's the proof of the forward implication. Converse, maybe later. Okay, so I think now what I want to do, I want to wrap this video up with a little bit of me finding a potential function, okay? Because that's probably about where we are right now. You know, eventually we're going to want to run integrals on these vector fields for reasons that if you're in physics C, you already know. We're going to want to line integrate, we're going to want to surface integrate, and that's going to kind of be the focus of this unit is really on the computation of these things, these line integrals and surface integrals, eventually. So, for example, I've got some function, and I want to find the potential function for it. So, saying it was 2xy and x squared minus y. All right, and I'm going to need a new piece of white chalk because this one's just completely worn down. Okay, so really at its core, this problem is very similar to like an indefinite integral in single variable calculus. We're trying to kind of find an antiderivative in a sense. So what I'm going to say is that, you know, if this thing is the potential function, then 2xy is equal to fx, and x squared minus y is equal to fy. So I could say that in one sense, it's kind of going to get us a little system of equations. So in one sense, f is equal to the antiderivative of 2xy with respect to x, which is going to be, okay, that's going to be x squared y plus any sort of like function of y, right? Anything that's constant with respect to x. So I'll call it maybe h of y, okay? But on the other hand, I also have that f is equal to the antiderivative of x squared minus y with respect to y. Okay, so what I'll get is an x squared y minus 1/2 y squared plus, I don't know, some function of x. And now I'm going to kind of look at this, take a step back and look at this and say, really, f is a function that fits all of these requirements. Okay, so I'm going to point out that really, I've got my h of y. I have found it. Okay, it's right here. And g of x, if it was, say, like not a constant, say it was some function of x, I would need to see it over here, right? Or I would need to see evidence of, you know, if I took the partial of this with respect to x, I'd have 2xy plus 0 plus 0, but all I have is 2xy. So I need this to be a constant. And so if we don't see a matchup, and we have to think about what happens when we take these partials, I know that g of x is going to be some constant c. So in conclusion, I've got this potential function f of x and y equaling x squared y minus 1/2 y squared plus some real number. And I think that's going to be all for this video. In the next video, I'm going to talk to you about vector fields in space. I'll kind of have an equivalent, kind of check to see if a vector field in space is going to be conservative. It's just, as you might expect, an extra dimension. It's going to just add a little extra layer of complication. But it is going to have to do with partials being somehow equivalent. And so I think that'll be all for this video. And just, I don't know that there's going to be a whole lot of homework assignment for this. I think maybe just, a couple of problems of, sketch the vector field, find the potential function. That's really all, determine if the thing is conservative or not. That's really all we're able to do at this point.